And it should be recording. All right, exercise 1G. So we've watched part 1 and I got you to analyze. I didn't want you to memorize all of these functions here, but just to get a vibe of, well, how would you analyze it? What restrictions do you see in each of the functions? And as you're exploring it, what do you take out of that? Because whatever you take out of it for yourself, that'll be helpful for when you're doing your Saxon exams. The questions your textbook won't get you to go this far. Okay, so that was just me trying to get you to analyze. Then the last bit, which I haven't sort of mentioned or highlighted to you, on this sheet that I've handed out, strictly increasing and strictly decreasing are two very common terms in the exam. So they want you to analyze a function and then determine which part of the function is what they call strictly increasing or strictly decreasing. Sometimes they ask you to justify it. The definition for what does strictly increasing mean? Literally here, so it's saying if you choose on your x-axis, I'll just draw an axis for you to see, x2 is bigger than x1. So it means that if x2 on the x-axis is larger than x1, so you've got a larger x value than the previous one, and that corresponds to if you found the y value of x2, so y value of x2, let's say at this point, y value of x2, if this point is larger than the y value of x1, so you can see here, x1, so I pick this point here, and this is now y1. If this is true, so these two, you can see there, the x2 is bigger than x1, and y2 is also bigger than y1. That's what these first two bits are saying. This is considered strictly increasing. Another way to look at it as well is if the derivative is positive. These are things that you can prove or justify. So if they ask you to justify, you need to say these definitions. Strictly increasing occurs when x2 is greater than x1 and y2 is greater than y1. And you can also prove it through the derivative as well. Okay, so that's one of the first things. Now, why is that put in the exam, and why don't they just say when is the function increasing? Because there is a difference when you start doing stationary points or derivatives. See the graph, you can get something like this. And let's just say the turning point is at 3, 4. So when they ask you, if I ask you now, when is this function increasing or decreasing? The notes are just there. Grab one each if you haven't. We could clearly see from the graph, this left-hand side for any x value less than 3, so from negative infinity all the way up until 3, okay? Now the question is here, this is the key part why they put in the exam. Is it inclusive or not inclusive if I'm asking for increasing? Because clearly it's getting larger and larger and larger as I'm choosing x values larger, so it makes sense. This yellow region is increasing. But when you write the domain, when they ask you for what x values will this function be increasing, they'll fix it to say strictly increasing, do you include or do you exclude the 3? Because when we come to derivative, when we're saying the function, we don't include the stationary point because we say right at that point the gradient's 0. But before that, the gradient is positive, right? So because it's positive, you would say this is increasing. So do you include the 3 or not include the 3? You had your hand up, Sarush. You actually do include the 3. And that's one of the key differences. If they say strictly increasing, you include that 3. Okay, and that's where the common mistake, that's why they chuck it in. It's 1 or 2 marks. If they say strictly increasing, you do include it, and it follows this theory. What is the definition? We said if x2 is greater than x1, so at 3, it is bigger than 2.1, for example, or 2.9. And is the y value at that point bigger than the previous value? Yes, it is. Okay, so this is the key part. Now, I know it says here, and dy dx is greater than 0. Okay, that's when we're pretty much looking on this left-hand side, but at the very end, that's the difference. Whether you include it or you don't include it, that's what when they say strictly increasing or not. Okay, so that's the only part that I found that in the exams they often use that, and it's whether you include or you don't include. That makes it confusing. Most students don't include. Okay, and I think it's that confusion where we start talking about the derivative being 0, derivative not being 0. That's one of the reasons why. Okay, so same thing with the decreasing part as well. Same with the decreasing part. It's just whether that endpoint, whether you include or don't include. So I thought it's worthwhile just having these as part of your notes. Write that down, strictly increasing and decreasing. Then there was a second part as I was going through your questions in your book, and I know it covers it again in chapter 7, but I just thought if you hadn't practiced it as well, sometimes they ask you, is it odd or an even function or neither? And there's a definition for that. I'll write neither up here. Okay, so when you get a function, no matter what it is, they usually start off pretty easy. It's not because of the power, so you don't look at whether it's got an even power or not. There is a definition for odd and a definition for even. And in this chapter 1G or exercise 1G, you're meant to pick up some patterns when there is this even power and then it's an even function. There's some properties to it that is nice to know. So let's go back. Odd. Does anyone remember from year 11? What's the definition for you to prove mathematically that it is an odd function? What was it again? Krish. F of x is equal to f of negative x. This is close. Okay, so that is the definition for an even function. So what it's trying to say, okay, now I'm going to rewrite this just because the way you're reading it, I'm going to explain what it means. What you just described is if I sub in a negative value into the function, if it ends up being exactly the same as the original function, this is called even. Here's an example. F of x is equal to x squared. Okay? So, if I subbed in, so this is the if bit. If I sub in negative x into the function, I will get negative x all squared. But the square root of negative x actually ends up being x squared, which is actually the same as the original function. See that? So the original function, that's what I defined. If I sub this in, and it turns out to be exactly the same that fits this definition, f of x is equal to f of negative x, these two here, so I'm going to highlight in blue. This equals that, which is this definition here, we call that even. Why is the even function useful? Because even functions, hopefully you picked up from 1G, that's an x squared graph. What happens when I go to x to the power 4, to the power 6, to the power of 8? What's changing? Anyone remember? Well, hopefully you explored it. Can anyone tell me what changes? Okay, what stays the same then? Everyone's a bit afraid. Okay, one thing, hopefully we picked up, x to the power 4 should still look like a U shape, but the difference is, what's that intersection? There's two intersection points. What must they be? Very good. Negative 1 and 1, because when you square them, and 1 and 1. But then, notice that the green line, when I wrote x to the power 4, this gets flatter. That's what I want you to analyze and learn yourself here. But can anyone explain to me, since we're here, why does it get flatter between negative 1 and 1? So if I picked half as an example, why is it that when I square a half versus to the half to the power of 4, why does to the power of 4 get smaller? Yeah. Or, and that's exactly, if you think in a logical sense, you're multiplying half multiple times. So you're halving what you have even more than what you would have. So if I had a length that was 10 centimeters long, halving it gives me 5. But imagine I halved it another 4 times. Of course, it's going to get smaller. True? So in a logical sense, that makes sense. But another way to look at it is the function itself. If you think about it, half squared versus half to the power of 4, essentially 1 1 squared is still going to be 1, and 1 to the power 4 is still going to be 1. The only difference between them is 2 to the power 4 or 2 to the power 2. But every time the denominator increases, if you increase the denominator, okay, it's like saying you got $1 and you got 1 million people to share it to, everyone's going to get a very small portion of that $1. So it gets smaller and smaller. So larger denominator, the smaller the value. Okay? And that's why if I went up to x to the power of 100, if I asked you x to the power of 100, what would it look like? It'll still cross through negative 1, 1, 1, 1 here as well. The only difference is it becomes a really square base because it gets really small between negative 1 and 1. So it ends up looking like a rectangle. Oh, yeah, kind of half rectangle or open beaker. Okay? But what do we take out of that if we know it's an even function? It's symmetrical. Okay? They both, whatever's on the left side also reflects on the right side. That's one of that negative x and x exactly the same. So the y values grow the same. That's why it's symmetrical. And that's one of the things I wanted you to pick up as you're exploring them. Even functions have this symmetrical look, and then odd functions have an asymmetrical look. Same values, okay, whether you do 3 cubed or negative 3 cubed, same value, just different direction. So 3 cubed is 27, or negative 3 cubed is negative 27. So one goes up and one goes down. But if you flip it, then it becomes symmetrical. So here's your second definition. So you got 1. Make sure to write that down if you've forgotten that from year 11. The second one is f of negative x. So if you had a function and you sub in negative x into it, but it equals to the negative of your function, essentially a reflection, okay, that is considered an odd function. Have those two in your notes. So you should have strictly increasing, strictly decreasing, odd function proof or mathematical definition, and even function definition. There will be functions that don't fit in either of these, and that's why it's called neither. Okay, so there might have been a question or two on that. Chapter 7 does it again, but if you've forgotten that, just write it down somewhere so that when you start summarizing, you've got some key mathematical definitions to refer to. That's only when you need a proof or justify, which usually is in a SAC, less so in an exam. Okay? All right, and that's 1G for you there. That's just finishing off the 1G that I thought worthwhile as you're revising and running through it. Because remember the core exercises of chapter 1 were, which two? Exercise? E and F. 1E and F. One is composite functions. F is inverse functions, both of which is very core. If you can do those two, then I already know A, B, and C is sorted because you know your domain, you know how to sketch, you also know your functions. So if you can do E, that ticks off that bit. Then F, you have to know your functions in order to do inverse functions. So that's why those are your two core. If you're running out of time, focus on those two and then move forward. All right?